All right, we're here with day 15 on Advent of Code, Beacon Exclusion Zone. The gist of this problem is that we get some info about sensors and beacons. There is a distress beacon that is sounding, but we don't know where it is, and it's not being picked up on any of our sensors. There's a rule about these sensors that they only pick up the closest beacon. So we have to look through some examples and figure out in the row where y equals 2 million, how many positions could not contain a beacon? And this is kind of just starting us out for part 2. So the way I tackled this problem was the very first thing is to figure out how to calculate a sensor coverage distance. The problem statement has a little bit about Manhattan distances. And so all that is you take the absolute value of the beacon x minus the sensor x plus the absolute value of the beacon y minus the sensor y. And a position is in the range of a sensor if that distance itself is less than the coverage distance of the sensor. So, using that knowledge, we can theorize that a beacon that we don't know about cannot be present at a position if, first, that position already contains a sensor or beacon that we do know about, and second, that position falls within the coverage range for any sensor. Because if it's within that coverage range, then theoretically it would be the beacon that that sensor is detecting. A little more pseudocode on that. So we'll initialize a tracker variable like num positions to 0. We'll loop through all the cells in a given row. The problem states row 2 million. If that position, x and y value already contain a sensor or beacon, we continue. Essentially, we don't care about that position. Otherwise, we want to check if the position has coverage from any sensor. If that's true, we're going to increment our tracker variable, the one defined up here. If false, then we do nothing and just keep checking. So functions we're going to need to be able to parse our input and get our grid boundaries. We're going to need to check positions that have coverage. Sorry, we're going to need to be able to take an individual position and see if it has coverage from any sensor. We're going to want to see if that position actually already has a beacon or sensor. And we'll just define some logic to get the number of positions that cannot contain a beacon in a row. So long function name to really, basically that's the problem statement in a function name. Okay, so let's start with reading our file in. I'm going to zoom in just one more here. And then we will split that on the new line character to get lines. And we'll declare a type called sensor. This is just going to have, it's an object that has property x sensor, x beacon, y beacon, and a sensor coverage calculated per the equation above. Now let's define some variables that will help us build out our grid and know our boundaries. So we're just going to set these to infinity and negative infinity, and we're going to call math.min or math.max as we go through our input. The input looks like this. It has the sensor positions, the beacon positions, and then we will use all those positions to calculate a coverage value. So we'll end up getting something that looks like this when we parse our input. So let's parse the input. We're going to declare a new map right here at the top. And for each line within that lines that we got above here, we are going to do some string manipulation. So this is me just calling substring on the first, getting the index of the first equal sign and the first comma. And then we'll set we basically erase that and get the next one. So just using substring and index of to get the values that we need. We're going to parse those to a number using the parseInt function. And then we'll update our min and max trackers using the math.min and math.max like I talked about. And then we'll calculate sensor coverage for this sensor using the equation that I already talked about. The max coverage, we're also going to call math.max on that, just so that we can get the largest coverage value. This is also going to take range, or this is also going to come into play on our bounds, right? If we have like a sensor all the way to the left, we want to make sure that we're checking to the left of that based on its coverage value. Now we'll just put them all within the map and we'll return our map. So we can declare a variable called sensor map and just set that equal to the output of our parse input function. And I'll console log the min x, min y, max x, max y to see what we're dealing with, as well as the sensor map. Save that, open up a console here, and run. And you can see we have our sensor map built out, and the min x and min y values and the max X and max Y values. So our algorithm, we're going to kind of iterate from min X minus the coverage, the max coverage, all the way to max X plus the coverage. And then we feed in that Y value for itself. But these will come into play later in part 2 as well. Continuing on, let's go ahead and define those functions that we mentioned at the start. So when we check for a position that has coverage, we want to feed it an X position and a Y position, and we'll loop through all of the sensors within our sensor map. And we will check that the Manhattan distance calculated here is less than that sensor's coverage. This is just a console log that I was using when I was debugging to show me which sensors had coverage, or sorry, which positions had sensors from which sensor. And so if it does fall within that coverage area, then we return true. Otherwise, we return false. Next, we're going to define our function check position has beacon or sensor already. This also takes in an X position and a Y position. We'll loop through all the sensors in our sensor map. If the X position is equal to a beacon X position and the Y position is equal to a beacon Y position, we return true. We'll do the same thing for sensors. If both of those don't prove true, then we'll return false. All right, so this is the one that's going to get us our answer. Get num positions that cannot contain a beacon in a row. We're going to pass out an input of a row, and we'll let num positions equal 0. We'll loop through all possible X values, so that's from min X minus max coverage to max X plus max coverage. And we will increment by 1 for each iteration. We're going to first call our check position has beacon or sensor already. If it does, then we continue. We really don't care about that spot. We already know about it. Otherwise, if the position has coverage, then we want to increment our num positions tracker. And at the end of that loop, we will just return num positions. So I'll log the range here just again so we get an idea of which X values we're iterating over. And I will log the result of this function with the passed in of a value of 2 million, like the problem statement asks. We'll save, come down here. Why can't I see? There we go. And run. And it's calculating. We get, what is this? 4,951,427. Let's come in and check 4,951,427. Part 2 was quite a doozy. This one actually wants us to find the distress beacon, which we don't know about, but we know a lot of places where it cannot be. And the strategy for this one, I have an Excalidraw. I went to the subreddit and found that there's really only one position in everybody's input that is allowed. So the way to find that is you have, say, 4 sensors that are all adjacent. And what we really care about is these 2 sensors that are adjacent and these 2 sensors that are adjacent. And the strategy is to find a line that can be drawn, a diagonal line that can be drawn based on the space between these 2, and one that can be drawn this way, which should be parallel to the coverage zones. And then we want to find this right in here. That's the intersection. That is the point that we're looking for. And then we can return the tuning frequency based on the values of those points. So I'm not going to belabor this. Otherwise, I'll be talking for probably 20 minutes. So for part 2, like I said, had to look at Reddit for this one. Find the location of the distress beacon by. First, we'll find the adjacent sensors that don't overlap, meaning that their Manhattan distance of coverage differs by 2. So that's talking about this distance right here and this distance right here. So we should get 4 sensors total from that. Then we'll find the equation for those lines that I drew. We should get 2 lines. We'll find the intersection of those lines and return the tuning frequency, which is 4 million times the X position plus Y. Close down our terminal. So apparently I just did it all in one go. The big thing to note here is we have this find adjacent sensors. What this does is it loops through the sensors map twice, and it gets the sensor coverage for the first and the second one. Notice that J starts at 1, I starts at 0, so this is looking at 2 sensors next to each other in our map. And we calculate that, what's it called, Manhattan distance here. And if the coverage of 1 plus the coverage of 2 plus 2 is equal to the distance that we calculated up here, then we'll push both of these sensors onto our array tracking the adjacent sensors that are 2 apart. So then we're going to call that function here and make sure that we can get all of our adjacent sensors. Let's see if I delete this and save. We run that. It's calculating part 1. And then we have, so this is sensor pair 1 here. And we should have sensor pair 0 up here. So we have our 4 sensors. Let me bring this all back. I have a function, well, I have a type here called line, and this is going to take an X and Y position. And then we just want to know if that line goes up and to the right or down and to the right, basically the slope. And I wrote a function called find line between that takes 2 sensors, and it just is going to calculate that line value. So I'll let you read through this on your own. We do have a conditional here, whether it's an upright line or a downright line. It's just going to look at the sensor positions really to know which way is which. And then we'll return the position and direction, which is our line of our type line. I have a function to get the line intersection. Needed some help with this one from Reddit. But essentially what we're doing is we have our 2 lines, and then we're projecting them on each other and getting our X and Y coordinate. And lastly, so we'll call the find lines from adjacent sensors. So then we have them. I'm just console logging them here so you can see them. And then we'll call get line intersection to get a point. We'll pass in each point for that. At the end, we'll log the point so we can see it, and then we'll finally log the tuning frequency here. If I save and bring it up, here we go, and run. It's going to run part 1 first and then part 2. So you can see this is our first line here. This is our second line here. This is the intersection point, and this is the tuning frequency. Check that is right. And that's the answer provided there. We get 2 gold stars, and I will see you for day 16. Thanks. Bye-bye.
Yeah.